Greetings and welcome to class. In this section, we're going to talk about conductors. Conductors are one of the more misunderstood areas of the code. Many questions deal with conductors and hinge on determining the correct size conductor and ampacity of conductor. So let's see what we have. Let's get busy. So let's start off talking about parallel conductors. And just to start at the start, what parallel means is instead of having one big wire to be able to satisfy my load, I'm going to connect on each end a smaller conductor, maybe a conductor that does not have the ampacity, meaning it's not large enough to carry the entire load by itself, but whenever I put it together with 2, 3, 4 conductors and I connect it together at each end, like this demonstrates here, then it's able to carry my load. Kind of think of it as most simple terms is if I had a 5 amp load and I had a lot of 1 amp wire, if I put the 5 1 amp wires together, that could carry my 5 amp load. So that's really what parallel means. That's what this is talking about. So here are the rules. There's very specific rules for parallel conductors. So first off, it says, is a general rule, 1/0 and larger, meaning the example I just used having 1 amp wire and a 5 amp load, that would not be applicable because it's too small. So typically and generally, we'll say that we start off with a 1/0 and larger conductor. Next rules here we see conductors must be, in each phase must have the same type characteristics, meaning to be the same length. And this is to the T, they got to have the same distance and same length of each conductor. Same conductor material, meaning I can't take some of them aluminum and some of them copper and mix them all together. They got to all be the same thing. Have the same size and circular mill area. So I can't take a 500 for 2 of them and a 1/0 for the third one, or any other combination of conductors. Each phase, whenever I say I'm parallel, for instance here I'm parallel 3 times, all of these conductors have to be the same size, same length, same material, same insulation type. So I can't mix those either, meaning whatever insulation is on this one has to be on this one, has to be on this one. Must terminate in the same manner. What that means is whatever method we've used to connect the wire to the terminal, we got to do them all the same. I can't have a big blue wire nut on one of them and a crimp connector on the other one and a pressure connector on the other one. They got to all be the same thing. And so this last part says and this is trying to avoid inductive heating, that all of our conductors, the code tells us in 300.3 and in 300.20 that we have a metal raceway here. I have to put all these conductors together and the grounded conductor and any equipment grounding conductor so that I don't induce current, or I have a magnetic field that I really induce into these raceways to create heat or induction heating. So that's why you see each of the phases comes into each one of the raceways. Instead of having all the A phase here and all the B phase here and all the C phase here, I got to put a little, one of each, so that what happens is they cancel out each other's magnetic field so that there's no net magnetic field around these, in this case, 4 conductors, and they don't induce a magnetic field into this metal raceway causing heat due to the induction. Okay, conductor ampacities, and remember ampacity is the maximum amount of current that a conductor can carry under the conditions of use without exceeding its temperature rating. So this kind of gives us an example here. Whenever we look at the ampacity of a conductor, you see we have the metal part, whether it be copper or aluminum, and then we have the insulation on the outside. Now this says that we have a number 4 AWG, that stands for American wire gauge. So I have the same amount of copper in each one of these examples, but look at how much current each one can carry, and look at the temperature rating associated with the insulation on each conductor here. So as we can tell, the higher the rating of temperature on the insulation, the more current, the more amps that each one of the conductors can carry. So really, if we think about it, whenever we're determining how much current can carry in for each one of the conductors, we're really determining how much the insulation can stand more than the actual metal conductor, whether it be copper or aluminum, how much they can carry. So really it's all hinging on how well this insulation can carry this current and how much it can carry. So that whenever we look at ampacity, you see that the rating associated with the temperature, and we'll see these values here, 60, 75, and 90, in table 31015 B16. This is your most common table that you'll use. You notice there's more. They go all the way through 31015 B21, but the one you use most often is right here, 31015 B16. Now, here's another table here that is used occasionally, and it's moved to the very back of Article 310, and it used to be up at the front by these, really before these tables, but now it's buried way back in the back. But it gives you a lot of detailed information about the conductor, meaning what's the size range, what type of insulation, what's the temperature rating, what's the conditions it can be used in, so forth. So that's a very, a lot of information inside of that table, although sometimes it's often overlooked because it's been moved to the back of the article. Okay, this is table 31015 B16. And you notice it says formerly table 31016. This is what it was for a long, long time. So what this is the amount of ampacities for insulated conductors. And let's read this. This will tell us all about this table. Sometimes we overlook this. It says rated up to and including 2,000 volts, 60 degrees C. You notice we said that a while ago, 60. There's 75 would be in here, and then 90 degrees C. Now here's the key part. All the numbers in this table, all these numbers are based on these conditions right here, these two conditions. Meaning, if I have a condition that says not more than 3 current-carrying conductors in a raceway, cable, or earth directly buried, and the ambient temperature, and what that means is the temperature surrounding the conductor. The temperature directly surrounding the conductor is not greater than or at 30 degrees C or 86 degrees Fahrenheit. Now, as things change from these conditions, then these values here change also. That's really what we're looking at. So let's look and see how we read this table. This table here, as we see, go across the top, it gives us the 60, 75, and 90. And you notice it says it again, 60, 75, and 90. Now you notice there's a little bolder line here. And what this does is it separates the copper conductors from the aluminum or copper-clad aluminum. So really you see 60, 75, 90 copper, 60, 75, 90 aluminum. These are the different types of insulations for that temperature rating. The 60 degree C insulation type is a TW or UF. 75 degree C would be a THW, for instance. And a 90 degree C would be a THHN. Same for the aluminum. Same insulation types, same temperature ratings. Now over here, we see the wire size. It goes from 18 to 2,000 kc mil. So from size 18 to 4/0 this is a 4. There's many pronunciations of these 4. I say 1/0, 2/0, 3/0, 4/0. Some people call them or pronounce it different. But these are gauges of wires, AWG. So this is a gauge of a wire. And then we get to right here, 250 all the way to 2,000. That's the actual circular mil area, kc mil. Remember the K stands for 1,000 circular mils. So that's what that means. This is 250,000 circular mils. This is 400,000 circular mils. So these are our wire sizes. And then over here on this side, these columns tell us how much current, what's the ampacity of each of the conductors under these conditions. Okay? So if I said I have a 1/0 conductor in the 60 degree C column, it can carry its ampacity as 125 amps. In the 75 degree C column, we're at 150. And in the 90 degree C column, we're at 170. So again, that is assuming I have a raceway with not more, or a cable, with not more than 3 current carrying conductors, and I'm installed this in a temperature, a surrounding temperature of not more than 30 degrees C or 86 degrees Fahrenheit. So that's how we read this table. Okay, we talked about current carrying conductors, and a grounded conductor is another name for what we slang term often call just everything the neutral, but this is a current carrying conductor also. You know, a neutral sometimes is, a grounded conductor is always considered a current carrying conductor. Whenever we say we have a neutral, maybe it is, maybe it isn't. It all depends on the conditions. So how do we identify this conductor, this grounded conductor, from the other ungrounded conductors or from the equipment grounding conductors? So that's what Article 200.6A, and you notice down here B, they give us direction for identification of the grounded conductor. So basically what it's telling us is, if you have a conductor, a grounded conductor, that is number 6 and smaller, it has to be identified by a white, gray, or an outer finish that's other than green with 3 continuous white stripes. So this entire length of the wire, meaning it's not okay for you to have, say, number 8, roll of black number 8, and then you take and put white tape on the outside or gray tape. It's not okay. If it's number 6 and smaller, now let's back up. I know you are going to say, oh, we do this on the job all the time. But remember, leave your job site stuff at the job site. This is for what's the minimum requirement of the code, and in this case, this is a little stronger requirement of the code than what you've done on your job site often. So make sure that you know what this requirement is. It's saying that this wire, if it's a grounded conductor or a neutral, if it's number 6 and smaller, it has to be white, gray, some color other than green with 3 continuous white stripes along its entire length. No tape is allowed. So that's what it tells us in 200.6a. In 200.6b says we got options. We can either do the same, meaning let's say that I had a 250 kc mill that I ordered in gray or white. That's fine. It can be that gray or white along its entire length. But the code says if it's number 4 and larger, it's okay for me to use identification tape or marking tape at each termination point. Excuse me. So that's the difference in where the size breakdown is. Number 6 and smaller, white along the, or gray, or again the 3 white stripes along the entire length. If it's number 4 and larger, it can be white, gray, 3 continuous stripes along its entire length, or you can mark it with tape at each termination. Okay, this is the whole installation of a conductor and how we can determine how much a conductor can carry. It all depends. Remember, a conductor is just not out there in the free air somewhere and not connected to anything on each end. It's connected to something on both ends, and sometimes connected together many times throughout the middle. So each terminal point has a associated temperature rating with it, okay? And so whenever you look at an entire circuit, you almost have to look at it like, what is the weakest link? Meaning, how strong is this chain? That's the old saying, right? How strong is the chain? As strong as the weakest link. What is the ampacity, or what is the rating of this circuit? Well, it has to be based on the weakest link in the circuit. So let's look at this example here. We see a 60 degree C termination here, a 75 degree C termination here, and I have a 90 degree C wire. So now, can I just take this wire at its value from the 90 degree C column and then say, well, I'm going to carry a lot more current than what the rating associated with this terminal or this terminal is, but my wire is okay in the middle. Is that all right to do? And the answer is no, because I have to base it on the whatever the weakest link is. So now I see these three different temperature ratings. I'm going to have to size this wire according to the 60 degree C column, because it is the weakest link inside the chain. This is what 110.14c is telling us. So if it's 100 amps or less, marked number 14 through number 1, then I have to use the 60 degree C column to size my wire by. Now the exception to that is if I have a wire that's smaller, or I'm sorry, that's number 14 to number 1, but let's say my terminals were rated, like this example, it says that I have a 75 degree C terminal on each end and a 90 degree C wire. Now I can use the 75 degree C column to determine the ampacity of this conductor. So you notice, because this terminal went from 60 to 75, the amount of current, the ampacity of the conductor went from 70 to 85. So it's really a big puzzle. You know, it all fits together, but it can never be more than whatever the weakest link is. So remember that, 110.14c. Now this is 100 amps and less. Now let's look for terminations rated over 100 amps. And basically what this is telling us is whenever we're over 100 amps, then we got to determine it based on the 75 degree C column. I know some of y'all are thinking, well, what if I have 90 degree rated terminals? Well, those are really not readily available, not very common to see on any type of equipment. So most every terminal that you see either is rated 60 or 75 degree C. Most of the wire we see is rated 90 degree C. So really, our ampacities of our conductors have to be based on, again, that weakest link. So probably 9 times out of 10, it's going to be out of the 60 or the 75 degree C column, depending upon all the terminations that fall within the circuit. Okay, now we said that we had a conductor. It's in table 31015B16. We have a not more than 3 current carrying conductors in the raceway, a temperature rating of an ambient temperature of not more than 30 degrees C or 86 degrees Fahrenheit. But now those conditions change. So what do we got to do? Something has to give, right? More than likely, you will increase the number of conductors in the raceway, more than 3. More than likely, the surrounding temperature of the conductor will increase instead of decrease. So whenever these happen, whenever either one of these conditions or both of these conditions occur, then we have to look at 2 tables, 31015B3A and 31015B2A. So this is whenever I have more than 3, here we go, more than 3 current carrying conductors in a raceway or cable. I use this table, 31015B2A, whenever my ambient temperature exceeds 36 degrees Celsius or 86 degrees Fahrenheit. So this is the table for my ambient temperature correction. Now you notice on this side is the temperature in Celsius. On this side is the temperature in Fahrenheit. And then here are my 3 temperature ratings of the conductor. Now, it makes no difference whether it's copper or aluminum. It's whatever the insulation rating is. And so the way this table works is you will, let's say that I had a 25 degrees Fahrenheit ambient temperature, and I had a 75 degree C conductor. So I would say, Okay, 125. It falls in between 123 and 131. A 75 degree C conductor is here. That means that conductor has to be derated by a factor of 0.67, meaning if I have a 100 amp wire under normal conditions, meaning 30 degrees C or 86 degrees Fahrenheit, if I put it in this much higher temperature, instead of being good for 100 amps, it's only good for 67 amps. So we're derating or discounting or correcting our conductor to match the conditions of the temperature. That's what this is here. Let's say that I had a conductor, a 60 degree C conductor in a 34 degree Celsius. I would say, okay, between 31 and 35, have a 60 degree C conductor. I'd line these two up. 0.91 is my correction. So if I had a 100 amp wire, under those conditions, 34 degrees Celsius, 60 degree C insulation, that wire would now be good for 91 amps. So again, I've derated or discounted this conductor to match the conditions of the temperature. Okay, let's do an example. So let's see what is the allowable ampacity of 4 number 10 THHN copper conductors routed through an attic in an ambient temperature of 120 degrees Fahrenheit. So we don't know any temperature ratings of any terminal, so we're just going to base our values off of the insulation type because we know nothing else. And the wire is already, size is determined for us. So I want to find the amperage of the conductor, so I'm going to go to table 31015B16, and I'm going to go to the 90 degree C column and determine that the ampacity of a number 10 THHN is 40 amps. Okay, so now because I'm in a higher ambient temperature, I need to find a correction. So I go to table 31015B2A, that's the table we just finished looking at, and I'm going to say my correction for 120 degrees Fahrenheit is 0.82 or 82%. So now I'm going to punch some buttons. 40, and that's the ampacity of the wire, times 0.82, which is my correction factor from table 31015B2A. That'll give me an answer of 32.8 amps. So now the maximum current that conductor can carry under these conditions has been limited now to 32.8 amps. It's no longer 40 amps because, again, that temperature has increased. So that's how this table and these corrections and adjustments work for temperature. Now this table 31015B3A is adjustment factors for more than 3 current carrying conductors. So whenever I'm inside of a raceway or a cable, and if I have more than 3 conductors, and what this is for is anytime I have a current carrying conductor, that conductor is generating heat. So as we pack more and more conductors in there, not only do we have more heat being generated, but also have less opportunity to dissipate or get rid of that heat. So this is why we have to, again, correct, derate, adjust, discount, whatever you want to call it, the conductor. So you notice the more conductors I put in the raceway or the cable, I'm just going to say raceway to make it easy, but the more conductors I put in the raceway, look at my percentage. If I have, remember, between 1 and 3, there's no correction. But whenever I go past 3 of them, remember that table 31015B16 said not more than 3 current carrying conductors. So once I go past 3 of them, I have 4 to 6 is 80%, 7 to 9, 70%. Look what happens whenever you put 10 or more, 10 to 20, 50%. So as an example, if I had a raceway with, let's say, 11 wires and they had a ampacity of 100 amps, because I have put so many wires inside of this raceway, that 100 amp wire is now only good for 50 amps. So this makes a huge difference. So these values here, again, the more we go, the the more we discount that conductor. And remember, this is based on current carrying conductors. So sometimes that neutral conductor is considered current carrying. Grounded conductor is current carrying. Our equipment grounding conductor is not current carrying. So that's what, whenever it says 3 current carrying conductors, that's what that means, the ones that are actually generating heat. So let's do an example. So let me get to here. I left out this part. I meant to mention this just a minute ago. Whenever we look at a raceway, and this relief is given to us back in the notes to Chapter 9, whenever we do raceway fill, it'll tell us that if I have a raceway that's 24 inches or less, then I don't have to worry about how many conductors and discounting them or derating them because of that. So let's say I had a raceway that was only like 6 inches long. Well, it's open on each end, and I guess the code feels like, or the makers of the code feel like, that I'm not going to really keep all that heat in there and damage the conductor. So it has an easy way or path to dissipate the heat. So this rule applies to a conductor that's over 24 inches. So often you'll see in the code that they'll call a raceway that doesn't exceed 24 inches a nipple. So whenever a conduit nipple is in place, meaning it's 24 inches or less, then this factor for fill, meaning whenever I go over 3 conductors, that does not apply. Now the temperature correction always applies. That conduit can be 1 inch long and it applies. So whenever you see the length of the raceway, let me get this. Whenever you see the length of a raceway included in a problem, that's not just trying to throw you off your game. They're giving you some information to let you know, okay, it's more than 24 inches long, so this, because there's 9 of them, I do need to apply the correction factors in 310.15b3. So make sure that you're aware of that. That's not just useless information. Now, if this would have said 12 inches, then, show's over. We don't have to worry about it. It's just the 9 of them, 19 of them, it makes no difference. But whenever it's 12 foot, that's over 24 inches, so we got to apply the demand. So first step, find the ampacity of the conductor, or what's the amperage of the conductor. So we go to table 310.15b16 and a number 12 THHN. Remember, we use the number out of the 90° C column because we don't know anything else. I don't know what terminal, anything else. If they would have told me 60° C terminals, then I would have had to put another number here. I would have determined this ampacity out of the 60° C column. Now I can use this higher number to correct with, but I would have to initially size the wire out of the 60° C column if that was my weak link in the circuit. So 30 amps, we say find the adjustment factor. I have go to 310.15b3a. 9 conductors says it's a 70% correction. So we take and do some math. My 30 amp wire, because I put 9 of them in this raceway, now is only good for 21 amps. So again, another big difference. So that is the maximum, that's the current, the ampacity. That's what it's limited to under these conditions. Now, what if I had a high ambient temperature and a conduit that had more than 3 current carrying conductors in it? Well, let's see how we handle that one. So what is the allowable ampacity of 6 current carrying number 14 THHN copper conductors routed through an ambient temperature of 105 degrees Fahrenheit? The raceway is 78 feet long. So this is telling us it's not a conduit nipple. It's over 24 inches. So I have to apply, all the table. I have to apply every demand that's there. Remember, it always applied for the temperature, but because the 6, if this would have been 7.8 inches, it wouldn't have mattered. It would have been considered a nipple. But because it's 78 feet, I got to correct for more than 3 current carrying conductors. In this case, we have 6. more than 86 degrees Fahrenheit. In this case, it's 105. So let's see how we do. We've got to do both of them. So first off, I'm going to find what's the amperage of the conductor. Number 14, THHN, again, out of the 90 degree C column is 25. The adjustment factor for 6 conductors is 80%. The adjustment factor or correction for 105 degrees Fahrenheit is 87% or 0.87. Whenever I do the math, I come out with 17.4 amps. So this wire really, almost half or close to half of what it started with. So took away quite a bit. Okay, continuous loads. What a continuous load is a load that's going to be where the maximum current is expected for 3 hours or more. So throughout the code for service, feeders, branch circuits, the language is very similar for all of them. It'll tell us that whenever we size a conductor and whenever we size an overcurrent protection device also, meaning a breaker or a fuse, that it will be based on the non-continuous load at 100%, meaning just whatever that number is. If it's 10 amps, then it's 10 amps, meaning it's not going to last for 3 hours or greater. So we just use that number. But then it'll tell us to take the continuous load times 125%. So if you notice, this is where we see this at. Now, a lot of times in the field, we have 2 different ways to approach this. And even on an exam, we have 2 different ways to approach this. So there's some numbers, different numbers that we'll use, and it all depends on what we're looking for. So again, review these areas. Again, this for branch circuit, feeder, branch circuit, feeder. Excuse me. These are conductors. This is for the overcurrent protection device. So this is what we need to talk about here. It all depends on what we're trying to accomplish. So if I have a known load, meaning and let's say that you know the load is 16 amps. It's a continuous load, meaning it's going to last for 3 hours or more. This is the language we see in the code, 125%. So what it's telling us to do is take 16 amps times 125%, and that equals 20 amps. So I would base the ampacity of my conductor for 20 amps, the rating of my overcurrent device, 20 amps. I can put 16 amps of continuous load on a 20 amp overcurrent device. The reason that's true is because most of our overcurrent devices are not rated for continuous use. So we cannot load them up to their handle rating is what I call it. Meaning that whenever you look on the handle of a breaker, it says 15, 20, 30, 40, whatever it is, you cannot load that up to all the way to that value with continuous load. I mean, it's going to last for 3 hours or greater. So that's why the code says, well, whenever you put that continuous load on this overcurrent device, then you can't load it all the way up to there. You can only load it up to a certain point. So that's why they tell us on this side that if I know what my load is, I mean, it's there, it's given to me, I'm going to take that load and do just like the code said, and those numbers are in there, 125%. Now, sometimes, so that's why I put the verses, I have a known breaker, and I want to know how much stuff can I put on it. How many lights can I put on this? How many machines could I put on it? How many receptacles? Whatever the case may be. So now I'm going to take this 80%, and 80% is the reciprocal of 125. So this is nowhere in the code book. Nowhere does it tell us 80% anywhere. This is just something we have to, we did the math. We know that if I increase this by 25%, I can decrease this by 20% and look at the number. I get the same thing. So this is where I have a breaker and I want to know how much stuff can I put on it. Well, I'll take a 20 amp breaker, find 80% of it, and come up with 16 amps. That's the maximum amount of continuous load that I can put on that overcurrent device. So again, it all depends on where you're coming from. I wouldn't want to take a breaker and multiply it times 125%, right? That wouldn't be correct. Same way I wouldn't want to take this load and discount it by 80% either. So, you know, it all depends on what you're trying to accomplish. So if we're trying to load up a known size of circuit with how much continuous load can I put on it, this is my direction here. If I have a load that I know and I want to know what size wire or overcurrent device, then I increase this by 25%. So it all, again, both of these ways are correct. It just depends on where you're coming from. Okay, now these are common questions that you see on an exam. This is support for vertical runs of conductor. And this is, again, still on conductors. So we go to table 300.19a. And what this does is gives us direction and methods for supporting conductors. And so we can see a wedge here. And again, think about a vertical run, meaning we're going up and down this way. So, man, with nothing else to help hold that wire, we know that, especially this copper wire, it's very heavy. We go up in multiple stories or multiple feet, then that wire is just hanging by its terminal, which isn't a good thing. You know, over a period of time, it may come loose. The whole thing may come tumbling down. So that's what the code is saying, that every so often, depending upon how big the wire is, you gotta do something to support this wire. So there's some options here. A wedge to really kind of fix it into place to where it can't move. Insulating support to where I'm going to hold the wiring steady. Or deflection, meaning I'm going to have some kind of non-conductive surface that I'm going to kind of wrap the wire around to where really if you think about it, the weight is being supported right here. You know, even though this does have some tug, it's not like if it was coming out of this raceway, you know, here where we could damage the conductor. So this table tells us how often we have to support this conductor dependent upon how big it is. Remember, vertical raceways. So if I have these small conductors, 18 to 8, they can go 100 feet. Now look, 6 to 1/0, and the number got bigger. 200 feet for aluminum, but for copper we stayed the same. We keep going. Look, copper, man, copper is much heavier, isn't it? We can kind of tell. We only went 20 more or less feet, but wow, we went down a little, 80 feet, 135 and 60. And now look over here, when we get to over 750, we need to do something every 35 feet. That's really almost like every floor of a multi-story building, isn't it? Or we're getting close. Or every 85 feet for aluminum. So that's what this table, it's not as dressed up as this. This is colored up a little bit, so don't expect it to look like that. But that's really what it's telling you, is how often in a vertical run, remember, vertical is going up and down, horizontal is going like the horizon where the sun comes up and goes down. This is telling us how often we need to support that conductor. So review all these code references that we saw in here. Go back through. Again, this is one of the areas of an exam that is often misunderstood, and a lot of questions about it. So make sure you go back and review each one, and I think this will hopefully help you in the right direction on understanding conductors. Thank you so much.